Okay, it's 8:30, so let's go ahead and get started today. All right, good morning, everybody. How's everybody doing today? Have a good weekend? No, this was good. Any Laker fans in the building? We got to see the Lakers win their 17th championship yesterday. Although I was a little bit worried after Game 5, though, not gonna lie, but I'm glad the Lakers could pull it out yesterday. All right. Okay, so the plan for today is I have one more kind of small point that I wanted to cover today on linear momentum, which we didn't get to do at the end of lecture last week. So, and it's a small point, and I know there's been some questions about the kind of the signs of certain things. So I want to make sure I cover that. And then after that, we're going to continue on with our discussion of control volume analysis, and we're going to continue today with angular momentum. So kind of the angular counterpart to the linear momentum part. Okay. Before I start today, are there just any questions? I know that a homework's been posted. Are there any questions on that homework or just anything we covered last week that I can answer before we get started? Okay. Okay, so I want to do one more point based on linear momentum, because I didn't get to do this last time, and it's kind of a, I think it might clear up some confusions about the signs on the homework, okay? And so if we write out the expression for linear momentum, okay, and of course, since we're talking control volumes here, this is the Reynolds transport theorem version of it. So this is linear momentum RTT, okay? We have sum of all the forces is equal to partial t, integral rho u dv, okay, that's the unsteady term, plus the inflow outflow term. Okay. Okay. And of course, most of the time for momentum, and we're going to apply this today for angular momentum too, we're going to assume this term is 0 because of steady. Okay. And so anytime you see steady, basically anything that has a time derivative like that is going to be 0. Okay. So what I want to talk about is actually this guy over here. Okay. Okay. Or in other words, how do we interpret this force, right? And so we went over last time that through Newton's second law, that in order to change the momentum of an object, you have to apply an external force. Okay? But if you kind of remember from your physics classes, you know, the interpretation of this force is something that's really important. Okay? And so how do we interpret this force for fluid mechanics? Right? And so what I want you guys to remember when you're applying this RTT is that this entire expression right here, this expresses the conservation of linear momentum for the fluid. Okay. Okay. And so the forces that you compute through this expression over here on the left, okay, that means this force that you compute is actually a force that's being applied on the fluid itself. Okay. Okay. And so it's not the force that's on the structure, it's not the force that's on, you know, an object, it's actually the force on the fluid. Okay. And so if you have a situation where the fluid is accelerating, right? So you consider one point to another point, and the fluid is going from a lower velocity to a higher velocity. That means the force that's on the fluid has to be in that same direction because you're accelerating the fluid that way. Okay. So let me just draw kind of a very simple example of this. So let's say that we have a nozzle. Okay. And let's say this is 0.1 and this is 0.2 right here. Okay. Okay. And there's the flow rate at each of the locations. Okay. And since, you know, just from the picture here, we know that A2 is less than A1. What this tells us is that U2 is greater than U1, right? And so in order to satisfy conservation of mass, the flow has to speed up in order to get through this, this smaller area, okay? And so what that means is that there is an external force that's applied by the nozzle going in the direction of the flow, okay? Okay. And so basically in order for the flow to speed up, there has to be a force that has to be applied on the flow, because you remember, we're changing the fluid's momentum, okay? But this is different than, you know, you might see some terminology from the problems that's like what is the anchoring force, or what is the reaction force, right? Because we know that from physics that anytime we have a force, there's an equal and opposite force that's going in the opposite direction, right? So if there's a force that's being applied on the fluid going from left to right, there has to also be a force being applied from right to left, right? Just because, you know, there has to be an equal and opposite force. And where does this force gets applied? So this is the force that the fluid imparts onto the nozzle. Okay. So in other words, the green force down there is the force that the nozzle puts onto the fluid in order to speed it up. And then the purple force up top, that's the force that the fluid imparts onto the nozzle as kind of like the, you know, the equal and opposite force, right? And so it's, you know, it can be a little bit confusing as to, you know, how you interpret these forces, but that's how you do it, okay? And so one thing that's even more confusing is that you might be asked to say, you know, say that this nozzle right here is being held in place by like a stand, right? Okay. And so let's say that this nozzle is fixed by these two guys right here. Okay. And so you might be asked to compute what is the anchoring force of the stand on the nozzle. Okay. Okay. And so you might be asking, you know, what direction is this force going to go, right? And so the vocabulary here is really, really key. So, you know, so we know the green force is the force that the nozzle puts on the fluid, and the purple force is the force that the fluid puts onto the nozzle, right? So in order to basically hold the nozzle in place, the anchoring force has to basically cancel out this purple force right here, right? And so the anchoring force is actually going to go from left to right in this case, right? Because the anchoring force is responsible for holding the nozzle itself in place. Okay. So it's a lot of kind of, you know, sometimes I even when I'm doing these problems, I kind of psych myself out and kind of switch the signs maybe one less time or one more time than I need to. But you know, this is kind of the basics of how you kind of interpret the force. But you know, the most important thing, you know, besides kind of the trickiness of the wording of problems sometimes, is that I want you guys to understand that when you're computing the force directly from RTT like this is the force that's on the fluid itself. Okay. And then in order to get the proper sign for the, you know, the force that you're end up solving for in the problem, you have to kind of look and kind of read very carefully about what's the how does the problem describe the force. And so is it the force that the solid object puts on the fluid, or is this an anchoring force that is on the solid object itself? Or are you solving for the force that's actually on the fluid? So it's a lot of kind of mental, you know, gymnastics. And, you know, I know it can be pretty confusing, but I think if you kind of take it apart and kind of remember this, you kind of go back to this part of the lecture right here and you kind of pick it apart carefully, you know, it should kind of help you interpret these forces, okay? Okay, so that's kind of the last thing that I wanted to cover from last week. And it's kind of nice that we had more time this week because it is kind of a confusing thing to go over. But are there any questions on this before I move on to angular momentum today? Okay. Okay. So now that we're done with mass and for linear momentum, we're going to get into I call this kind of the sequel for control volume analysis. And so this week we're going to be doing angular momentum and energy. Okay. Okay. And so we're going to follow the same procedure that we did last week. We're going to start with the general form for a Reynolds transport theorem. Okay, so let me write that down first. Okay. And so first we have our production term. And so that's, total derivative of big B, right? And this is equal to the unsteady term or the accumulation term. Okay. That's over the entire control volume plus the inlet and outlet term. Okay. So same RTT. And then what we're going to do now is we're going to plug in, expressions for big B and little b. Okay. And so what is big B for angular momentum? Okay. And so big B in this case is actually going to be a cross product. Right? There's going to be the cross product of the radius, okay, or the moment arm, crossed with m times the velocity vector. Okay? And so this right here is angular momentum. Okay? And we'll say it's angular momentum of a particle. Okay. And so just like we always do, now that we have a big B, or actually let me label these. Okay? And so distance, this is a distance vector. From the particle to the axis of rotation. Okay. And this right here is the velocity vector. Okay. And so just like we always do, in order to get little b, we're just going to divide this by m. Okay. And so little b is just going to be r cross u. Okay. All right. All right, so the last thing that we need to do before we plug these into Reynolds transport is we need to define production, right? And so we have to ask ourselves, how can angular momentum be produced for a particle, right? And so we know that for linear momentum, we can produce linear momentum by applying an external force, right? And so the angular equivalent of this is we can apply an external moment or an external torque. Okay. 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 And so if we can apply an external torque on an object, that's what's going to produce angular momentum in a fluid. Okay. All right. Any questions on this before we write out the full RTT for angular momentum? Okay. All right. So let's go ahead and write out the expressions. We have the sum of the moments, external. Okay. And then we have our accumulation term. So we have partial t, integral of rho, and then we have r cross u dv, okay, plus our inlet outlet term. And so we have integral of rho r cross u dot n dA. and this is over the control volume, and this is on the control surface. Okay. So this is kind of our full expression for conservation of angular momentum. Okay. Okay. And so just like we did with linear momentum, you know, we're going to mostly assume steady conditions. Okay. So we're going to take this term to be 0 here. Okay. And so we're going to assume steady most of the time. And by most of the time, I mean all the time. Okay. And so we're basically just left with, you know, the sum of all the external moments is equal to the inlet and outlet, or the inflow and outflow of angular momentum into the system. Okay. Okay. And so, you know, we've done RTT, you know, quite a few times. So I think, you know, there's not much else to say about the interpretation. And so I think, you know, I think at this point it'll be useful just to do an example just to see how this is actually used in practice. Okay? So let's do an example. Okay. And so let's say that we have a sprinkler head that's going to be watering a lawn. And this sprinkler head is one of the ones that spins. Okay. 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 Oh, actually, one thing before I forgot to mention this in the first page, is, you know, let's just briefly mention, you know, what are some applications where you would apply this equation like this, okay? Because, you know, I don't know what your guys' memory of angular momentum is, but I remember when I learned it first in physics, you know, the fact that you have kind of this cross product of vectors, you know, is always kind of really confusing to me. So I really didn't like doing that, doing angular momentum, and that feeling still kind of persists today. So we're going to do this one example with angular momentum, but, you know, I'm not going to do too much with it because it's, you know, it's still kind of breaks my head sometimes too. But, you know, it is actually really important for fluids because there's a lot of fluid mechanical devices that rotate. Okay. Okay. And so one that's, you know, pretty obvious is that, you know, if you have one of those ceiling fans, you know, like those ceiling fans, they often rotate. Okay. So that's a pretty common one. Other common devices that rotate could be like a pump. And so if you've ever seen like a big industrial pump, you know, those things rotate, and that's how they basically, you know, add power to the flow. And we'll talk about that more once we get to conservation of energy. Okay. And so kind of the opposite of a pump is actually a turbine. Okay. And so we'll talk about the differences between pumps and turbines later. But basically, you can think of a turbine as a way to extract power from a fluid. Okay? And again, those are one of the things that turn and spin. Okay? And also, of course, like if you ever looked inside the inside of a commercial airplane engine, you'll see that that's a rotating device as well. Okay? So there's lots of you know, interesting fluids applications for angular momentum. Okay, so let's get back to our example. And so one more application is your garden sprinkler, although it's not as ubiquitous as fans, pumps, turbines, and engines. So, you know, it's kind of gotten left off the list, but it makes a really good example problem here. Okay, so I'm going to draw kind of two views for the sprinkler because it's kind of a three-dimensional object that's kind of hard to view otherwise. Okay? And you'll have to excuse my lack of art skills. Okay. Okay. So this would be kind of like the side view. Okay. And so from the side view, I like the side view because you can see that the water is being fed up here. Okay. So the water goes actually up the shaft of the sprinkler. Okay, so that's like Q in. Right? And then we can draw a top view or like an overhead view. And you can see it actually looks like this. Okay. And so from the top view, you can see here that the water is going to come out just like that. Okay. It's going to come out the other side too. Okay. All right. So just like we always do with these control volume problems, our first step is going to be to actually draw our control volume. Okay. 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 And then we're going to draw it on the other view too. Okay. And remember, we want to draw this such that the control volume or the surface where the water comes out is going to be perpendicular to the velocity, so we have less things to compute. Okay. Okay. Any questions on just the setup of the problem or just the image? Does this kind of make sense? Can everyone kind of view the sprinkler in 3 dimensions about what this kind of looks like? Okay. Okay. And so let's put some numbers on this. So let's say that water enters a sprinkler through the bottom at a constant flow rate. Okay. And so let's say that Q in is going to be equal to 0.001 meters cubed per second. Okay. And each of the nozzles out on the sprinkler head, and so there's going to be 2 of these, but each of these have an area of 3 times 10 to the minus 5 meters squared. Okay. And so just shorthand for that, we're going to say 3e minus 5. Okay. Okay. And so another thing that we can say is that the distance between the sprinkler heads and kind of the middle shaft is going to be 0.2 meters. And we'll say that this is distance between sprinkler head and rotation axis, or we'll say shaft. Okay, and so that R value that I just mentioned right there will be this distance right here. Okay, and so the distance from the shaft to the outlet right there. So that's basically gonna be our moment arm that we're gonna apply on angular momentum. Okay. Okay, so with those parameters, let's state that we want to solve. And so in part A, what we want to solve for, let's say that the sprinkler is totally staying still, so it's not rotating, okay? And so in order to do that, there has to be some torque that resists the angular momentum from the flow. Okay? And so first, let's compute the resisting torque. Okay, the resisting torque that's required to keep the sprinkler still. Okay. And so in part B, we're gonna solve for the resisting torque again, but in part B, we're gonna let the sprinkler head rotate at a speed of 500 revolutions per minute, okay, or RPM. Okay. And then finally in part C, we're gonna say that we're gonna have no torque at all. And so when no torque is applied, we wanna solve for the rotational speed or the angular velocity. Okay. And so to do this, we're going to apply, first of all, we're going to apply conservation of mass, and then we're going to apply our conservation of angular momentum, just so you guys can kind of see it in action. Okay. All right. Any questions on this? Okay. So let's go ahead and start solving. Okay. So let's start with part A. Okay. And so in part A, let's actually start with conservation of mass. Okay. Because right now we know the inflow of the water into the sprinkler, but we don't know the velocity of the water that's coming out the sprinkler heads. Okay. So let's start with that. So we have 0 is equal to partial t rho dv plus, and I'm just going to go ahead and plug in, our expression for the inflow outflow. Because we know for the inflow outflow, we can just say that this is going to be the sum of the of the mass inflow minus the mass outflow. Okay. And so since we're doing an angular momentum problem, we know that this is going to be steady. Okay, so we can say that this is going to be 0 right here. Okay. And so when we write this out, then we get that m dot in is equal to m dot out. Okay, as is the case with steady conditions. Okay, and if we write this in terms of the flow rate, we say that rho times q in, which we know is equal to rho q out. Okay, and since we're working with the same density here, both the densities are going to cancel out. All right. And so in this particular case, we know what. Oh yes. And so in this case, we know what q dot in is, so that's fine. Okay. And so we're going to solve now for q dot out. Okay. And so q dot out, or the flow rate out, this is equal to the sum of the flow rates. The sum of the flow rates for the two nozzles. Okay. And so the way that we can compute this, we can say that this is equal to U nozzle, A nozzle. Okay. But since there's two of these guys, we can add another one of these. Okay. So this is U nozzle, A nozzle. Okay. And so what we have here is Q in is equal to 2 U nozzle, A nozzle. Okay. And so the only unknown here is U nozzle. Okay. So let's go ahead and solve for that. And so we can say that U nozzle, or U out, okay, is equal to Q in divided by 2A nozzle. Okay. If you plug in the numbers, this is equal to 16.67 meters per second. Okay. All right. And so you can see in this problem, even though now that we're doing angular momentum, conservation of mass here is still really useful. Okay, because almost no matter what conservation law that you use, momentum, energy, angular momentum, you're going to need to know what the velocity is at every inlet and outlet to your system. Okay, and the way that you usually solve for those velocities is through conservation of mass. Okay? So in this case, we didn't know what the velocities at the two nozzle outlets are, or the two sprinkler heads, and so the way that we solve for that is through conservation of mass. Okay? And so now that we know this velocities, we can plug that into our conservation of angular momentum. Okay. All right, any questions on this part right here? Right, so
yeah.
question. Oh, go ahead.
So we're just stating, well, we're setting it up that the mass flow rates are equal to each other, and then with that, we can state that both Q's are equal to each other?
Yes. Yeah, because the mass flow rate is just equal to rho times Q, and since the density of water is not changing in the control volume, then those are the same.
Yeah, basically conservation of mass. But I was curious about since we have one set equal to the other, um, we're looking for the U nozzle,
Yes. Yeah. Yeah.
and we can just find it from either the inlet or outlet.
So when I say nozzle, what I mean is in particular the outlet nozzle. Right. So we're actually not given in this problem what the area of the intake right here is, and
Okay.
actually it's not important because it's not going to contribute to the angular momentum. And so what I
Okay.
mean by U nozzle, what I mean is this guy right here.
Okay. Okay. So then for the QN, the U nozzle, A nozzle is technically the inlet nozzle.
That's the outlet nozzle. Yeah,
Oh, it's
but
the outlet nozzle.
right. So but they have to be equal to each other because of conservation of mass. Yeah.
Okay.
Yeah.
Okay. So then we just basically replace the Q out with the QN just to find the outlet nozzle. Then, right?
Exactly. Yeah.
Okay.
Yep. All right. So the question is, why not M out minus M in for conservation of mass? Oh yes, thank you. Yeah, that was a typo for me. It should be M out minus M in. Thank you. Mm-hmm. Absolutely right. So why is there a 2 in the Q equation again? So the 2 comes from the fact that Q out is equal to 2 of these guys right here, right? Because we have two nozzles. And so what I did was since these two are the same, I just combined them together to 2 U nozzle, A nozzle. Yeah. Yeah, because we have 2 outlets here. We have one on the bottom here, and then we have one on the top right here too. Yeah. Yeah. Exactly. Yeah. Mm-hmm. Yeah, because they have the same area, we assume that they have the same area, so then they have to be equal to each other. Okay, right. And so now that we have the mass, we can go ahead and plug this into conservation of angular momentum. Okay. And so let's go ahead and just cancel out the steady term because or the unsteady term because we know we're in a steady situation. Okay. And so we have the sum of all the moments. Okay. This is equal to integral of rho r cross u. Okay. U dot n. Okay. dA. Okay. Okay, and so before we begin, let's, I kind of just mentioned this briefly before. Remember this quantity right here, this integral quantity, we can say that this is the sum of the contributions to the angular momentum from all the inlets and outlets to the system. Okay. And so if we kind of draw just a very simplified, okay, I'll do a little bit better than that. Right? So here's our sprinkler head, okay? And we know that it's going to rotate kind of around this shaft right here, okay? And so if we take a look at our inlet, right? Our inlet is actually coming in up like that, right? And so remember, in order to have some kind of angular momentum, there has to be some distance in between the shaft and the velocity, okay? Because that's what this R right here represents. So this R represents the distance in between the velocity and whatever axis that we're rotating about, right? And so in this particular problem, our inlet is actually going right up the shaft. Okay? Okay? And so in this particular case, the inlet is actually going to make no contribution to the angular momentum because there's no distance in between the inlet and the shaft and the axis of rotation. Okay. Okay. And so that's why we didn't solve for the velocity at the inlet because we don't need it in this case. It's not going to contribute to the angular momentum. Okay? And so the only thing that we're going to consider is this is the outlets. Okay. Okay. And so if we evaluate this integral for the outlets, we get something like this. We get rho, we get sum of the moments is equal to rho. Okay. Our outlet area is a nozzle. Okay. Okay. So I'm just going to say a nos. Okay. And then we have our cross product. Okay. And then our carrying velocity. Right. And remember, since that there's two nozzles, we're going to set this equal to 2 right here. Okay. And our two nozzles are going to be identical. Okay. All right. So remember, this is a special case where we have two identical outlets, but when you're doing these problems on your own, make sure that you write this out individually for each outlet. Okay. Okay. And so let's start writing the terms here. Okay. And remember, so this u dot n, this is our carrying velocity, and so this is just the velocity of the fluid at the outlet, respecting the sign conventions for the inlets and outlets. So since this is an outlet, it'll be a positive u nos. Okay. And so that's what we just solved for in the previous part. Okay. And so that's going to be positive u nozzle there. Okay. And then now what we need to do is we need to compute this term right here, this r cross u. Okay. All right. Any questions on this before we compute this this cross product?
Could you repeat that about the carrying velocity again?
Right. So the carrying velocity, yeah, I see that it's lagging too. So the carrying velocity, that's going to be the velocity of the fluid at the outlet, but remember, it respects a special sign convention. So remember, for inlets, we take this u dot n to be negative, the negative of the velocity, but at the outlets, we take this to be a positive. Okay. And so since this is an outlet for the two nozzles, we're going to take this to be a positive u nos right there.
So that's our carrying velocity at the end, right?
That's our carrying velocity at the end. Yeah, so it's going to be a positive U nozzle because the fluid is coming out at the sprinkler heads. Mm-hmm. All right. Okay, so let's go ahead and compute this guy. All right. And so we know from previous classes that whenever we take the cross product between two vectors, we just simply get another vector. Okay. But in this case, since we just have one axis of rotation, we're just going to take the magnitude of this cross product. Okay. Right. So normally when you're doing these angular momentum problems, angular momentum is a vector just like linear momentum. And so you need to sum up normally you have to perform the angular momentum in each different directions. Okay. But in most cases that we're going to talk about in this class, there's only just going to be one axis of rotation. And so when you take that cross product, you're only just going to take the magnitude of that vector. Okay. And so when we have this r cross u right here, okay, and we just simply take the magnitude, and so the magnitude is just going to be simply the moment arm, or r, multiplied by the velocity. Okay, so this is going to be r, which we're given in the problems. Remember, this is going to be 0.2 meters. Okay. Okay, and this is going to be multiplied by u nozzle. Okay. Okay. And so that's the magnitude of this vector. Okay. But as with everything that's kind of confusing with control volumes, the tricky part is deciding what sign do we choose for this. Okay, so do we use positive or negative? Okay. Okay. And so for cross products, the way that we determine the sign is with our right-hand rule. Okay. Okay. So everyone's familiar with the right-hand rule. We've seen that before from previous classes. Okay. So we'll talk about it kind of just briefly again too. Okay. And so the way that the right-hand rule works is that you need to consider both the directions of the vectors that you're taking the cross product of. Okay. And so let me draw kind of an image of this. Okay. And so let's draw our sprinkler head from the top view. Okay. I'll draw kind of this way. Okay. And so the vector, this r vector right here, remember that's the distance vector between the velocity stream and the axis. Okay. And so in this particular case, I'm going to draw it off to the side here just so it's easier to see. Okay. Our r vector is given by this purple vector right here. Okay. Meanwhile, our velocity vector, since the velocity is coming out of this nozzle, is going to look like that. Okay. And so in order to do this exercise, you're going to have to take your right hand and you're going to have to maybe put it up to the screen. Okay. And so in order to determine which direction the cross product points, what you're going to do is you're going to put your hand like this. You're going to make kind of like a finger gun, but then your other three fingers here, you're going to point in a direction that's perpendicular to that. You're going to take your index finger and point it in the direction of r. Okay. So in this case, the r vector is pointing kind of upwards to the right on the page. Okay. Remember, r is your first vector in the cross product. Okay. And then what you're going to do is after you do that, you're going to rotate your hand such that your three other fingers are pointed in the direction of the other vector. Okay. And so, right now this is extremely hard to do because we're virtual, but kind of maybe you guys do it with me. So if you point your index finger in the direction of the r vector, and since our u vector points down and to the right, I'm going to rotate my hand like this, such that my two fingers are going to point in like that. Okay. So index finger in the direction of r, three other fingers in the direction of u, and then whichever direction your thumb is pointing, that's the direction of your cross product. Okay. And so I'll do it up here just so you guys can see. And so since my thumb is kind of pointing into the page, or should be pointing into your screen like that, that means in those cases we take a negative sign. Okay. And so in this problem, we're going to take a minus r times u nozzle. Okay. All right. Any questions on that?
Yeah. So when the thumb is pointing out of the page, that'd be positive, right?
Correct. Yes. Mm-hmm. Yeah. And so I did this right-hand rule for one of the sprinkler heads here, but you can do it for the other one too. And what you should see is that it's also pointing into the page. Okay. And so if you haven't done so already, try doing it for the other sprinkler head. Point down, point your fingers that way. Don't sprain your elbow, and then you'll find that they're both going into the page in that case. Okay. And so now that we've determined the sign and we have everything else in the expression, we can finally go ahead and compute the moment. Okay. And so let's go ahead and put this all together. So our external moment, okay, it's going to be equal to 2 times the density times a nozzle. Okay. We're now going to multiply this by the cross product, so it's going to be minus r u nos. Okay. Okay, and we're going to multiply that by the carrying velocity, which is going to be a positive u nos. Okay, remember it was an outlet. Okay, and so this is equal to minus 2r rho a nos u nos squared. Okay, and so we plug in the numbers, and we get a minus 3.33 newtons meters. Okay. And so in order to keep the sprinkler head still, we have to apply an external moment or an external torque of 3.33 newton meters. Okay. All right. Any questions on that part up there?
Yeah, the moment. It's not the sum this time. It's just the the moment.
Yeah. So there's implicitly
Okay.
assumed to be a sum right there, but since there's only one moment in this case, so you kind of think it was the moment that the shaft is kind of putting on the sprinkler head. I just solved it just for one point.
Okay.
Yeah. Okay. So I know, the tricky thing in these control volume problems is always going to be the signs, because it's, there's so many different sign conventions here. So we have our Cartesian sign convention, we have our inlet and outlet sign convention for the carrying velocity, and now we have the right-hand rule for angular momentum problem. So it's hard. I know it's a lot to keep track of, but as long as you kind of take each term kind of individually, just kind of go slow, one term at a time, I think that's what makes these problems a little bit easier. So don't assume that one term will have the same sign convention as the next term. So you really kind of have to question each and every term in your RPT. Okay. So in part B, what we're going to do is now the sprinkler is rotating at 500 RPM. Okay. Okay. And so what we want to do is we want to solve for the torque that's required to maintain this 500 RPM. Okay. All right. So the first thing that we're going to do is, we have our rotational speed here as in revolutions per minute, but it's actually more useful for our calculations to convert this to radians per second. Okay, so let's go ahead and do that. So we have 500 revs per minute. First, we're going to convert the minutes. So we have 1 minute over 60 seconds. Okay. And then we're going to compute the revolutions to radians. We have 2 pi radians over 1 revolution. Okay. And this is equal to 52.36 radians per second. Okay. So this will be a little bit more convenient for our problems. Okay. Okay. And so now that we computed the rotational speed in radians per second, what we can do is we can actually compute the actual velocity of the sprinkler head. So this is not the velocity of the fluid that's coming out of the sprinkler head, but because the sprinkler head itself is rotating, now that's spinning at 500 RPM, we need to compute that actual velocity. And so we're just going to take the radius of this sprinkler and multiply by this rotational speed. Okay. Okay. So I'll call this here omega. Okay. And so if we do that and we say that this is 0.2, then what we get is 10.472 meters per second. And so that's kind of the you can almost think as like the linear speed of the sprinkler head that's kind of rotating around. Okay. And so because we have a sprinkler head that's rotating here, you know, and that's the part where the fluid's actually coming out. So you can kind of think of it like the sprinkler head's moving this way and the fluid's kind of coming out this way, okay? And so in this problem, we have something that's similar to the thing we did at the end of Wednesday's lecture, where we have a moving control volume. Okay. And so this velocity that we just computed right here is actually going to be the velocity of the control volume. Okay. Okay. And so what we need to do now is we need to adjust our RTT to account for this moving control volume. Okay. And we're going to do it just in this exact same way that we did for the linear momentum problems.
Quick question: what's the W? Does that work?
That's omega. So that's just the rotational speed. So that's
okay.
That's what we did up here. Yeah. Mm-hmm. Okay. Any other questions on this? Okay. Okay. And so let's write out our RTT for angular momentum again. Okay. So we have moment external. Okay. Sum is equal to rho r cross u. Okay. Times u dot. And so we know that when we do angular momentum problems, we have to replace one of these velocities. We have to replace some of the velocities here with the relative velocity. Okay. And so not to be confused with the angular velocity from the previous one, remember we used the symbol W here to denote that. Okay. Okay. And so you can see from this expression here, we have two velocities, right? So we have the velocity that's in our angular momentum expression, so that's our r cross u. And we also have a velocity from the carrying velocity. Okay? And so it turns out the only velocity that we're actually going to replace with W is going to be the carrying velocity. Okay? Okay? And the reason for that is, remember this expression right here, this is an expression of the angular momentum of the fluid, okay? Or the absolute angular momentum of the fluid, okay? And so it doesn't make sense to replace this with the relative velocity because we're not transporting relative angular momentum through our control volume. What we're doing is we're transporting absolute angular momentum, okay? And so, it's if you kind of go back to kind of our linear momentum, kind of at the beginning of where we started to that derivation, you'll see that we did the same thing where we only replace, this guy, the carrying velocity with the relative velocity. Okay? I know that we did some algebraic manipulations in order to get, W over here on the left as well, but this is kind of before that. Okay? And since now we have a cross product instead of simply just the linear velocity, we're not going to change that r cross u right there. So we're only going to replace this velocity here with a W. Okay. 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 And so let's go ahead and continue with the problem. Okay. And so what we need to solve for now is we need to solve for both W and U. Okay. So the only thing we have right now is VCV, or the velocity to control volume. And so now we need to compute W and U. Okay. Okay. And so our first stop, just like always, is going to be conservation of mass. Okay. So even though we're rotating now, we still have to preserve mass. And so from conservation of mass, if we actually write out the entire expression, okay, for a moving control volume, what we get is the following. Okay. So our conservation of mass expression is not going to change. We're still going to have the same amount of inflow. But when we solve our conservation of mass expression for a moving control volume problem, what we get from that is the relative velocity, so W. Okay. And so our W vector in this case is going to be 16.67 meters per second. And so that's what we solve for in part A. Okay. Okay. And so now that we have W, we can simply solve for U. Okay. So U is simply just going to be W minus VCV. Okay. And this is just the definition of the relative velocity. Okay. And so if we plug in the numbers, so we have VCV from the previous page, and we have W from up here, and we get that U is 5.93 meters per second. Okay. Okay. All right. And so once we plug that in, so we can plug both of these velocities into this top expression right here. Okay. What we get is the external torque, or the external moment, is equal to -2. Because remember, we have two outlets, 2 times rho times r, A nos, okay, U nos, W nos, okay. Okay. And this is equal to minus 1.19 newtons meters. Okay. All right. And so you'll notice that we have less torque in this case because, you know, we're not preventing the entire thing from rotating. We're letting it rotate a little bit, but, you know, we need to apply a torque just to slow it down a little bit, just so it doesn't reach maximum speed. Okay. All right. Are there any questions on this?
Yeah, where did you grab the 5.93? Was that just plugged in values from?
Yeah. Yeah, so I plugged in basically 16.67 in for W, and then for VCV, I plugged in the 10.472 from the previous page right here.
Right.
And so you take the difference in between them, you get 5.93. Okay. All right, so that's part B. And so now let's do part C. Okay. And so part C, we're going to say that we have no applied torque. Okay. Right. Okay. And so with no applied torque, what we're going to do is we're going to solve for, you know, the rotational speed. Okay. Or in other words, you know, first we're going to solve for VCV. Okay. And then from VCV, we can get the rotational speed of the spring. Okay. And so let's actually take our expression that we had right here. Okay. And let's start with that. But we're going to set M external equal to 0. Okay. So M external is going to be equal to -2 rho R times A out, U out, W out. Okay. And since we have no applied torque, we're going to set this guy equal to 0. Okay. So we have 0 is equal to -2 rho R A out. Okay. Okay. And so what we need to do here is, since we want to solve for VCV first, we need to rewrite one of these velocities in terms of VCV. Okay. And so since we have that expression for U out on the previous page, okay, so U out in this case is equal to W minus VCV. Okay. Let's go ahead and plug that in. Okay, so we have W minus VCV in for U out. Okay. And we have multiplied by a W again right here. Okay, so let's go ahead and solve for this. Okay, so since we have the 0 on this left-hand side, we can go ahead and divide by all the constant terms right there. And so we have 0 is equal to W minus VCV. Okay. And so we have W is equal to VCV. Okay. And so VCV in this case is going to equal to W, which is equal to 16.67 meters per second. Okay. And if we equate this to the expression for rotational velocity, so we know rotational velocity is going to be the radius times the rotational speed. Okay? And so to differentiate it from W, I've kind of give it a W rot. And so the rot stands for rotation. Okay? Okay. And so W rot is going to be VCV divided by R. So we're going to take our 16.67 here and divide it by 0.2, which is our radius. And then we get 83.35 radians per second. Okay. Okay. And then you can also, of course, you can convert this radians per second into revolutions per minute or RPM if you so desire. Okay. All right. Any questions on the end of this example right here?
Could you explain again why we canceled out our 2-row radius and our area out?
Sure. Yeah, so we cancel those out because we have a 0 on this left-hand side right here. So we can divide this entire expression by 2-row R A out. In this case, we cancel out another W right there. So if we do that for the same on the other side, then it's all just going to cancel out right then. Yeah. So we leverage the power of 0 to kind of cancel out a ton of our terms there.
Yeah, okay.
Okay. Right. So that was kind of a pretty long example, but I picked it because it kind of showcases kind of everything that you can do with angular momentum problems. So, we talked about the sign convention, and we talked about what happens if you have a moving control volume, and we had kind of this bonus part C right here, where if you have no external force, what are some of the things that you can solve for? Right? All right. So the question is, why is M external equal to 0? And so the M external was set to 0 was because in part C, we said that we have no applied torque, we have no applied moment. And so in that case, we set the external moment equal to 0. Yeah. And so that's from this part of the problem right here. Yep. Okay. And so there's one last thing that I want to just mention before we we move on. Okay. And it's kind of a transition into conservation of energy. Okay? And so with these angular momentum problems, we computed things like the torque and the angular velocity, but sometimes it's also interesting to compute power or energy. Okay? Okay. Right? Because in order to apply any kind of moment or any kind of torque, oftentimes you have to apply some kind of energy or power to the system. And so in particular for angular momentum problems, we call that shaft power. Okay. And so this is, this is going to be applied to situations where we have pumps. In order to make a pump rotate, we have to apply some kind of power to it. And this is the power that we do. Okay. And so in order to compute shaft power, we do the following. And so our expression for power is going to be W with a dot over it. Okay. Okay. And so the way that we compute it is we take T shaft, where this is the torque, okay, or the moment on the shaft. Okay. And this W right here is rotational speed or angular velocity. Okay. And so if you take the product of these two guys, of a torque and an angular velocity, what you get is power, right? And so what is the unit of power? Right? So this has units of watts. Okay. Okay. All right, so that kind of leads us into our discussion of conservation of energy. Okay, so I'm going to introduce it today, and then on Wednesday we'll do some example problems with it. Okay? Okay. And so this is kind of the last kind of conservation law that we're going to apply to RTT. And of course, energy is kind of one of the most important things. So, we kind of save the best for last in some cases. Okay? Okay, so we've already kind of seen an expression of conservation of energy for fluids, and that's when we did the Bernoulli equation, right? So when we did Bernoulli, we kind of talked about how the Bernoulli equation was kind of already an expression of energy, right? And so Bernoulli, we had our three terms. We had pressure, we had kinetic energy, and we had potential energy or gravity. Okay? And so those terms are going to make a comeback, but now we're going to put things in terms of control volumes instead of streamlines. Okay? And so this is not going to be that different than Bernoulli. So all the intuition that you have from Bernoulli equation is definitely going to be applied here. It's just that now we're going to apply it to control volumes instead of just individual streamlines. Okay. Okay. And so just like we talked about at the beginning, conservation of energy is really important to devices like pumps and turbines. Okay. And so those are the main two devices that we're going to be looking at. Okay. But actually, this conservation of energy for fluids, this is kind of the bridge that connects, what we're learning in this class in fluid mechanics to what you would learn in some of your other classes in the thermal sciences. So some of you might be taking thermodynamics this semester, or 304. Okay. Okay. And so there's going to be some connection to that, or at least some of the knowledge and intuition that you gained from thermodynamics will definitely be applied here. Okay. And then the other area where it's really important is actually heat transfer. Okay. So some of you might be taking heat transfer in the spring, okay? And so if you take heat transfer in the spring, you'll see some of these ideas come up, okay? And so, the main thing is that when you have a flowing fluid, we've talked about RTT can transport a lot of different things, right? Because it shows how the fluids can kind of transport things with its flow. And so, one of those things that can be transported is heat or energy. Okay? And so this idea that fluids can transport, energy or heat will be prevalent a lot in your heat transfer class. So, if you're taking heat transfer next semester or you're taking it next year, I want you to remember that from this class that, a fluid can transport heat or energy. Okay? And then when that happens, it's called convection. Okay? So you'll hear that term come up a lot in your heat transfer class. Okay, but let's bring this back to fluids. And so just like we always do with these kinds of problems, we're going to start again with RTT. And so with RTT, our first step is going to be to define what our big B variable is, our extensive variable, and what our little b is. Okay? So let's start with big B. Okay? And so big B in energy will be our total amount of energy here. So it will be E total. Okay? Actually, let me give myself a little bit more room because E total is a little bit big. Okay? And so our total energy here is actually going to be made up of three different terms. Okay? And so it's going to be a little bit different than our previous RTT examples where big B was just one thing. Now we have big B is equal to three things. Okay? Okay? First thing we have is the internal energy. So we have mass times energy internal. Okay? Plus, we have our kinetic energy term. So kinetic energy is going to be mass times velocity squared over 2. Okay? And then we have our potential energy. Okay? So this is internal energy. And so this right here is kinetic energy. Okay? And this last term right here is potential energy. And so those are the three kind of forms of energy that we're going to consider for RTT. Okay. Right. And so if you're not familiar with the concept of internal energy, you can kind of think of that as kind of an expression for the temperature of an object, right? And so if you have an object that's really hot, then we say that has more internal energy than others. Okay. So it's energy that an object can store that's not in the form of kinetic energy or potential energy. Okay. So most of the time that's expressed as temperature. Okay. All right. Any questions on this? Okay. Okay. And so that's our expression for big B. And so just like we did before, we're going to from this we're going to get our expression for little b. Okay. And so in this case, we're going to have it be little e because it's the intensive version of energy. And so just like we did before, we're just going to take big B, which in this case is energy total. Okay. Okay. And we're going to divide it by M. Okay. And so we get internal energy plus U squared over 2 plus GZ. Okay. Okay. And so that's our expression for big B and little b. And so just like we did before, let's talk about our production. Okay. And so we need to talk about how energy can be produced in a system. Okay? And so I know everyone's familiar with just like how mass can't be created or destroyed, energy also can't be created or destroyed. Okay. But we're going to do a little bit of a twist on this. Okay. Because remember, when we talk about production, we want to talk about how energy can kind of miraculously or spontaneously show up in a fluid. Okay. 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 So while it's true that energy can't be created or destroyed, we can take energy from somewhere else and actually put that into the fluid. Okay. And so we're gonna have energy in two different forms here. Okay. And so here's our expression for the production. Okay. And so this is gonna be equal to two different things. Okay. And so first we're gonna have a Q dot. Okay. Not to be confused with the Q that we've been doing before. So this is Q with a little dot over it. Okay. And then we're gonna have a W dot as well. Okay. And so let's define these two terms. Okay. Okay. And so if we have a heat transfer that goes into or out of the fluid, this is a way that energy can kind of show up into a fluid, right? So if you heat up, a pot of water over your stove, right? The fluid itself thinks that that heat is kind of coming into the fluid itself, and that's raising its internal energy, right? And so if we apply some kind of heat transfer to the fluid, either we heat it up or we cool it down, we're going to have some kind of a net energy production in terms of the fluid. Okay. Okay. And this W net right here, this is any mechanical work that's done on the fluid. Okay. And so just like, we can use heat to inject energy into a fluid, we can also use mechanical work the same way. So if we have a pump, we can turn the pump and that's going to put energy into the fluid, or we can have a turbine that extracts energy from the fluid itself. Okay. All right, any questions on that? Okay, so I think, this is a pretty good place to stop because it's 9:45. Okay? So when we pick this up on Wednesday, we're going to finish the expression. We're going to write out the full expression for RTT for conservation of energy, and then we're going to do some examples with it. Okay. Okay, but that's all I got for today. So thank you everybody for tuning in. I know it's getting to be the middle of the semester, so this is the part where it's a kind of a slog. So I appreciate you guys waking up early and coming to the lecture. And so, I'll stick around if there's any more questions, but if not, have a great day, and I'll see you guys on Wednesday.
Yeah, thanks, Professor. See you Wednesday.
Thanks.
Thanks, Chris. Yep, thanks, guys.
I have a quick question.
Sure, what's up?
It kind of goes back to the first thing you were talking about at the start of the lecture with the forces.
Yep.
So for the homework, when you're talking about the thrust force, are we essentially, we're taking the negative of that because we're focusing on what it's doing or what the fluid is doing?
Yeah, so you have to kind of read the question and ask what it's asking for. So in that case, the thrust, that's going to be the thrust that's on the jet ski. And so it's going to be opposite of the force that's actually been put on the fluid. And so since the force on the fluid is going to be negative, right, because the fluid has to accelerate from the inlet to the outlet, right? So the thrust has to be in the opposite direction. So it's going to be the positive of that.
All right, thank you.
Yep. Mm-hmm. All right, question. So what about the properties of fluid? Do we neglect it like acid? What do you mean? What do you mean by the properties of the fluid? Or are you talking about maybe like chemical properties of the fluid? Is that kind of what you're referring to? Oh, okay. I see what you mean. Yeah, in that case, we're going to ignore those interactions between particles. I think I kind of understand where you're going from this, because we're for these problems we're going to consider kind of the control volume as a whole. So any kind of like intermolecular, interparticle interactions or chemical reactions, we're not going to assume that. And if we do consider it, like I think we're going to do one example with like a heating pack, or maybe I'm thinking of a heat transfer class. We're gonna consider those as kind of like a net heat transfer, like kind of an overall effect on the entire control volume. So that those will usually be quantified for you, but we're not going to get into like kind of the nitty-gritty details of of that stuff, because that's more of a heat transfer. That's more of like kind of a chemistry kind